All right, so I want to go through a kind of a first basic maximization problem. So the problem is we want to maximize the quantity 10x plus 11y. This is called our objective function. And we want to do this subject to the constraints or the limitations that are allowed for the variables x and y. So we just have a system of linear inequalities that they must satisfy. So the idea is to find the value of x and y, which satisfies all of these constraints and also gives us the largest value of our objective function. So we start with very simply, we graph the solution of the system of linear inequalities. This is called the feasible set for a linear programming problem. When we were just graphing these, we just called it the solution region. But this set of points is the feasible set of solutions. In other words, these are the allowable choices of x and y that we can use to compute values of this objective function. And then once we do that, we can just find the vertices of all the feasible set and plug each of those into the objective function, and whichever one gives us the largest value is the solution. And really, it's what it is, it's the decision. So in practical terms, when we get to word problems later, the idea is to make a decision for the values of x and y to achieve the objective. So our feasible region, we graphed our four inequalities. Then we just graph the lines, find the region, which is this gray region, which is our feasible set, or the solution region of our system of inequalities. And we've got the vertices listed here, each of the corners of this region. We just need to plug each of those in to the objective function and see what values we get. So again, plugging 0 and 0 in, we get 0. Plug 35 and 0 in, we get 350. And you can see I'm doing this for all of them. The vertex, which has x is 29.41 and y is 27.94, gives us a maximum value of 601.44. Now later we'll talk a little more graphically why we can do this, but the basic idea is pretty simple. Whatever the value of z is, if you plug in a number for z, you get a line. And if you change the value of z, this line doesn't change its slope, it just changes its intercept. So we're basically choosing z as big as possible so that this line touches, in a sense, the highest point of the feasible region. But it's not necessarily the highest point. It's relative to the slope of this line. So we'll see a little bit more of what makes that work later. But in the end, what it means is the solution will come from one of the vertices. And it is possible that a solution could occur at more than one vertice. And if that's the case, then any point on any of the edges of our feasible region connecting any two vertices like that would also be a solution. So it is possible for linear programming problems to have a unique solution, or infinitely many solutions, or no solutions if the feasible region has no points in it.